Good morning, everyone. Hope you are all doing fine. Today's lecture will deal with aryl halides. What are aryl halides? We first studied earlier alkyl halides, which had a halogen attached to an aliphatic carbon, an aliphatic chain, and a halogen was attached to it. When we dealt with alkyl halides, we said that the halogen is more electronegative than the carbon. Accordingly, the halogen will carry a partial negative charge and the carbon attached to the halogen will carry a partial positive charge. Afterwards, we studied the phenomena of aromaticity, where we dealt with the benzene ring, and we said that the benzene ring consists of 6 carbons. Each is an sp2 carbon, and the compound is planar. We said that each one of these carbons has a py orbital perpendicular on the plane of the ring, and an electron cloud exists above the plane of the ring, and another electron cloud exists below the plane of the ring. Accordingly, if we try to combine all what we have just studied regarding the alkyl halides and the aromatic rings, combining these two together, we will end up with the aryl halides. These are halogens attached to a carbon, but the carbon they are attached to is a part of the benzene ring. They are aromatic compounds. There are lots of differences between alkyl halides and aryl halides. Why is that? In case of the alkyl halides, your halogen was attached to an sp3 carbon, and accordingly the bond between the halogen and the carbon was a regular single bond. There was no overlap between the lone pair of electrons of the halogen and any pi electrons existing in the side chain. However, in case of aryl halides, we have the lone pair of electrons of the halogen in a p orbital, which is parallel to the p orbitals of the benzene ring, and accordingly it is present in some sort of an overlap. There is some sort of an overlap between the lone pair of electrons of the halogen and the electron cloud of the benzene ring. What I mean to say here is that the lone pair of electrons of the halogen are not present on the halogen. They exist within the electron cloud of the benzene ring. They are part of the electron cloud of the benzene ring. Accordingly, this bond between the halogen and the benzene ring is not regarded as a regular single bond. It's a very tough bond to break. You cannot introduce a nucleophile like you used to do in case of alkyl halides and just substitute the halogen. This is not as easy as you used to do in case of alkyl halides. How can we perform such a reaction? We have to take care of some precautions. First of all, it's preferable if the halogen is a more reactive halogen. For example, fluoro is more reactive than chloro, than bromo, than iodine. So fluoro performs this reaction much easier than the other halogens, followed by the chloro. The nucleophile needs to be a very strong nucleophile in order to be able to attack and substitute the halogen on the aromatic carbon. Finally, it's preferable if you add electron withdrawing groups at the ortho and para positions to the halogen to produce a resonance that places a positive charge on the carbon directly attached to the halogen and accordingly facilitates the attack of the nucleophile. Let's see the class closely. First of all, we will deal with the nomenclature of the compounds. As we all know, any aromatic compound is named relative to the benzene ring. So these are halobenzenes. So this is fluorobenzene, chlorobenzene. So you will just nomenclate the aromatic compound like you have already learned how to name aromatic compounds in the videos of aromaticity. So refer to them. So you will just name an aromatic compound, and the halogen is just a substituent that is present on the ring. Just give it its correct numbering, and this is how you can nomenclate these compounds. As we have mentioned before, the lone pair of electrons of the halogen is present in a p orbital, which is parallel to that of the benzene ring, and accordingly the lone pair of electrons of the halogen exists in some sort of an overlap that includes the electron cloud of the ring, and accordingly this bond is not easily broken as in case of alkyl halides. As I've mentioned, to perform a nucleophilic substitution reaction, you need to take care of certain points, which is halogens need to be highly reactive, and this is the order of reactivity of halogens. You need to use a strong nucleophile, something like the alkoxides. These are very strong nucleophiles. And you need to introduce strong electron withdrawing groups like the nitro group in the ortho and in the para positions relative to the halogen to facilitate the reaction. Let's take a look at the mechanism of such a reaction. If you have the benzene ring and you have the electron withdrawing group, something like, for example, the nitro group, and you have the halogen, for example, the fluoro, which is the most reactive halogen. First of all, the resonance takes place, putting a positive charge on the carbon directly attached to the halogen, and then the strong nucleophile will attack this carbon, now carrying a full positive charge, facilitating the reaction. And you have just lost your aromaticity. As any reaction, as any aromatic reaction, you have to retain your aromaticity. How is that done? By the nitro giving back the electrons to the ring and removing the halogen as a halide, and the nucleophile now exists in the place of the halogen. This is how the mechanism of this reaction proceeds. So as we have mentioned, you have a halogen, preferably a small one like fluoro or chloro. You have a strong electron withdrawing group at the ortho and para positions. You have a strong nucleophile, such as the alkoxides, and you perform the reaction. You remove the halogen and you introduce the nucleophile. It's not an easy job. As we said, the nucleophile has to be a strong one. We have to use a reactive, highly reactive halogen, and we have to introduce an electron withdrawing group to the ring. As we have mentioned, the alkoxide will attack the carbon that carries a positive charge due to the presence of the nitro group, introducing a resonance that places the positive charge on this carbon, and then retaining of the aromaticity, giving you compound. This is how the nitro group will introduce the positive charge to this carbon, and this is how the charge present in the ring will be stabilized by the presence of the nitro group. This way we have finished aryl halides as a part of this semester's syllabus. Next video we will deal with the alcohols as the second class present in this semester.